The original Legend of Zelda game is a timeless classic that takes the casual player a couple of days to beat and the most experienced speedrunners just a little under a half hour. But a very intricate and complex glitch discovered by Sockfolder allows the player to execute arbitrary code they write in-game to beat the game in under 3 minutes. The summary of the route goes like this. Write the code on the name entry screen, go to the second dungeon, get the whistle, go to the graveyard, spawn 10 ghosts, wait until the conditions are right, pause until the overworld music reaches a certain part, unpause, press A and B at the same time, and, well, the rest is history. Yeah, it's pretty cool. So let's take a closer look at the route and carefully go through exactly what's happening as we go through the game and execute the ultimate Legend of Zelda glitch. So first we're going to write the code in the name entry screen. File names are stored in memory, and every character corresponds to a different byte in memory. We're naming the files weirdly because we're actually writing specific bytes to memory that will be executed as assembly code later. Our two limitations are that we only have 3 file names to work with, and we have to make the first 5 characters of one of the file names Zelda so we start on the second quest. We need to start on the second quest for reasons we'll go over later in the video. We named the first file Zelda because that's where it fits best. Now let's start up the game. Up until we get to the graveyard, the route really isn't different from playing the game normally at all. All we have to do is make sure we don't die twice, a death being either actually dying or continuing using the up A menu. We'll go over why when we look at our code later in the video. Anyway, after we get the whistle, we need to go to this screen of the graveyard to execute this glitch. The glitch works here because using the whistle spawns an actor that clears one of the gravestones to reveal a hidden staircase. This is essential for performing this glitch, and it's all because of sprite limits. The Legend of Zelda only allows for 11 sprites to be written on the screen at once. If you try to spawn a 12th sprite, the game won't let you. To execute this glitch, we actually abuse an oversight and spawn a 12th sprite. When you spawn the whistle actor, the game forgets to check to see how many sprites are on the screen beforehand. Since we've spawned all the sprites we can, the sprite spawns somewhere it shouldn't be, important memory is overwritten, and the game freaks out. There's a small table starting at offset 350 in memory that stores IDs of on-screen sprites. Sprites that spawn as soon as you load the screen spawn at the lowest sprite slots possible, which means sprites will start looking for empty slots to spawn into at offset 350 and working forward. When a sprite wants to spawn, the game looks for an empty value in the table to overwrite with the sprite ID so the game spawns it. Contrary to sprites that spawn when you load the screen, when you try to spawn a sprite, it tries to spawn in the highest sprite slot possible, which means it first checks whether it can spawn in slot 11 at offset 35A. If it can't, it'll check to see if it can spawn in slot 9 at offset 359. If that doesn't work, it'll check to see if it can spawn in slot 8, and so on and so forth. If all the sprite slots are filled, the sprite will give up and not spawn. However, because the developers forgot to put in the boundary check that tells the sprite to give up for the whistle actor, the game will keep looking for bytes with a value of 00 in locations in memory outside of the table to write the actor's ID to. But where does it look first? Well, this table is actually part of a larger array that holds information about sprites. When the whistle can't find a place to spawn at the beginning of the table, it loops back to the end of the array and looks for empty slots to spawn in. It just so happens that when we're in the graveyard, the end of the array contains values that correspond to ghosts' action states. So let's talk about ghost action states. The type of ghost that spawns when you touch a gravestone moves erratically. This is because what they do is controlled by behaviors determined by their action state. These action states can be any value between 0 and 5 depending on what the ghost is doing and are written at the end of the array containing information about sprites. Basically, all of these action states correspond to a location in a table of functions that dictate what the ghost does, and since the action states only go from 0 to 5, the table is only large enough to hold the instructions for those 6 action states. The important thing here is that action state 0 corresponds to the ghost accelerating. This is important because, when the whistle actor looks through the ghost action states for a place to spawn, it will fill in the first place in memory with the value of 0 that it finds. Since the ghost accelerating corresponds to action state 0, which is written as 0 in the code, the game mistakes it for an empty slot and writes the actor's ID there. Consequently, the game tries to execute the code at location 5E in the table. But since the table only accounts for action state values up to 5, the game instead runs garbage data way beyond the table as code. If we set everything up right, the garbage data will lead us to the code we wrote when we named the character files, and we'll go straight to Zelda and beat the game. Oh, and a quick note. To make the glitch work, we have to corrupt the third action state in the table. This means we have to execute the glitch when the third to last ghost we spawn is accelerating and every ghost we spawned before it is not. With that information, let's look at what happens when we execute the glitch. If we set everything up right, when the game tries to execute the data at position 5E in the table, it reads memory starting at offset 602 in memory as code. The memory at offset 602 and 603 has something to do with Link's action state, and we can control it. If we're just standing there, the values at these offsets will both be 0. But when we press B to use the whistle, the value at 602 will be 10, and when we press A to use the sword, the value at 603 will be 1. So if we press both of these buttons at the same time, the values next to each other will be 1001, which the game will interpret as the instruction branch if positive to 605. This will always execute, which means we will always jump to 605 in memory and execute the data there as code. The values of 605 and 606 will both be 0 if we don't have low health, and they'll both be 40 if we do have low health. These values being 40 writes an instruction that crashes the game, so we can't be at low health when we execute the glitch. The hex value 0 corresponds to a break instruction, and since they don't do anything here, we want the values to be 0 so we can keep moving along and executing code. Since we use the sword, we're going to end up executing the next function on an odd byte. The next instruction that isn't a break is actually at 608, but that isn't something we want. Since we use the sword, we actually skip over 608 and execute the function starting at 609 as code. The value of the byte at 609 will always be 10, which means we're dealing with another branch instruction. The value of the byte at 610 corresponds to the music. It tends to increase as the music loop plays, but sometimes it'll jump back down to a lower value. This means that to get the branch instruction we want, we actually have to execute the glitch at a certain part of the music. If the value at 610 is small, we'll probably end up jumping to a location in memory with the radically changing values. They change so erratically that we can't manipulate them in real time to get the instructions we want the game to execute, so branching here will almost definitely end up crashing the game. However, after these unsafe values is a nice safe bed of break functions, so we're going to try to branch to there. So we want the value at 610 to be larger, so we skip the unsafe stuff and end up executing the safe consistent stuff. If we make it to the break functions, we're almost home free. However, in this bed is the counter for how many times Link has died. If Link has died twice, this value will be 2, which creates an instruction that stops the game. This is why it's important that you don't die twice. Anyway, we eventually end up at offset 638, which is the first byte of the table where file names are stored. When we make it here, the game will execute the code we wrote at the file screen. So here it begins. The file names are stored in memory in order, which means the first bytes we're going to execute are the Zelda file name. Conveniently, the code this executes isn't important to the glitch, so we can safely get to the rest of the code. Since the Zelda name isn't important, let's step through what the rest of the code does. Right off the bat, we execute 3 pull from the stack functions. Whenever you call a function, it puts 2 values on the stack. These values correspond to where you were in the code when you executed the function, so the game knows where to return to when it's done executing the function. We start the code by pulling 3 values off the stack and end the code at the return function. We do this so we end up returning to where we were when we executed the glitch. That way, the game won't keep executing memory as code and eventually end up crashing. But before we get to the code that corrupts the memory and wins us the game, we need to talk about a few more values. The value at offset 10 in memory corresponds to what world we're in. If we're in the overworld, the value is 0. If we're in the first dungeon, the value is 1. If we're in the second dungeon, the value is 2, and so on and so forth. Since Zelda is in the 9th dungeon, we want this value to be 9. However, since we're in the overworld when we execute the glitch, the value will start at 0, so we need to find a way to make it 9. The value at offset 11 corresponds to something related to game state. If the game is loading, the value is 0. If the game is not loading, the value is 1. Since we want to load the 9th dungeon, we want this value to be 0. The value at offset 12 corresponds to a sort of substate. When a screen is loading, the value is normally 2. When the screen isn't loading, the value is usually 5. Since we want to be loading when we execute the glitch, we want this value to be 2. The last value we need to change is the one that corresponds to what quest we're on. The value at 62D corresponds to whether we're in the first or second quest with a value of 0 or 1 respectively. We start in the second quest, but we want to end up in the first quest because that confuses the game, so we also have to set the value at 62D to 0. This will put us in a weird hybrid of the first and second quests. We need this weird hybrid game mode when we execute the code for a specific reason you'll see when we go over what our code does. Anyway, with these goals established, let's move on to the code. First, we have the function logical shift right at 11. This function basically divides the value at offset 11 by 2 and writes the remainder to the carry. 11 is the location in memory that stores the value that corresponds to game state, and before this instruction its value is 1. When we divide by 2, we end up with 0 with the remainder of 1 due to integer division. The value 0 is written to offset 11, and the value 1 is written to the carry. Next, we have the function rotate left at offset d indexed with x. Since we overwrote the action state of the third to the last ghost we spawned, x is equal to 3. D indexed with x is equal to d plus 3, which is 10 in hex. So this function is rotate left at offset 10. This function multiplies the value at offset 10 by 2 and adds the carry. The value starts at 0. 0 multiplied by 2 is 0, and 0 plus 1 equals 1, so the value is written to offset 10. Next, we have another rotate left at offset D and x with x. X hasn't changed, it's still 3, so it's another rotate left at offset 10. 1 multiplied by 2 is 2, and since we used the carry already, its value is 0. 2 plus 0 equals 2, so the value 2 is written to offset 10. Next, we have a third rotate left at offset 10. 2 times 2 equals 4, and 4 plus 0 equals 4. The value 4 is written to offset 10. Our next instruction is logical shift right at 12. We start with a value of 5, so integer division gives us a value of 2 with a remainder of 1. 2 is written to offset 12, and 1 is written to the carry. Next is our last rotate left at offset 10. 4 times 2 equals 8, and since our carry value is 1, we add it to the product to get 9. Our last instruction before the return is logical shift right at 62D. The value here is 1 because we're in the second quest, and because we divide by 2, the value will be set to 0. This puts us in the hybrid quest. Then we execute our return function, and the game updates to match the game state we wrote in with our code. With that, the glitch is complete, and we'll load into Zelda's room. We load into Zelda's room because the hybrid quest confuses the game, which doesn't exactly know where to put Link. It just so happens that we load into Zelda's room, and with that, we've beaten the game. I hope this helps you get an idea of what's going on behind the scenes when we execute the Legend of Zelda Arbitrary Code Execution Game End Early glitch. Thanks for watching.